Chapter 19, entitled Monte Carlo Valuation, will continue some of the work we did in Chapter 18 on the log normal and binomial models, and will teach us an approach to simulating stock prices either at a specific point in time, which we might use to value a call option or a put option, as well as simulate prices over time, which we would use for other kinds of option valuation. This chapter will be presented in 5 modules, and the first module is just going to be a quick introduction to the notion of Monte Carlo valuation. So if you go back to Chapter 10, we developed a general formula for the price of a European option, and here in my formula I've represented it as a European call with expiry at time capital T, but this could be any European style payoff function payable at time T. And we're valuing this option at time little t, and we're going to assume that from the valuation date to the expiry date that we divide that time interval into n steps of size h. In this notation, in Chapter 10, we might have called it n steps of size delta t. The general formula we derived is the present value of an expected payoff. And what we see is that this is an expectation formula using the binomial distribution, that first of all we have a present value, that's clear enough for the time period involved. We have here the payoff function of the call option at time capital T as a function of the n+1 stock prices that we're assuming can prevail at that time. We have a binomial lattice which at time n steps produces n+1 prices, and those prices follow a simple format depending on how many up and how many down steps we have. We can see in the symbol for the payoff function that there are n+1 values of number of ups and number of downs. The total number of ups and downs, of course, has to be n, and that's why we have a general form u to the j, d to the n minus j, because the total number of steps has to be n, and it's only a question of how that's allocated. And then we have the binomial coefficients, the combinatorial factor n choose j, as well as the risk-neutral probabilities, and notice that the exponent of p star is the same as the exponent of u, because for every up step that occurs with probability p star, every down step corresponds or with a probability of 1 minus p star. So the exponents follow in this formula. So this is the formula for the exact price on a binomial lattice of a European call option in this case, and this formula was derived by using a replicating portfolio. Remember, this is not just a pricing formula. This is the way I would like to think about this is a formula that was algebraically derived to reproduce the price we determined using the replicating portfolio for the option. So the logic of option pricing from Chapter 10 was we replicate the option with a portfolio of stock and T-bills. The price of that portfolio could be determined, and we can then algebraically convert that price into this form where we can see that the price can be represented as the present value of an expected payoff. So we can just, as I just stated, express this price as a present value of an expected payoff. This is just a notational version of that more extensive formula. It says the price of the option is the present value of an expected payoff, where E star just denotes that this is an expectation using the risk-neutral binomial probabilities. So you might well guess, and this is the essence of Monte Carlo valuation, that if we could somehow generate a large random sample of stock prices at time t, and of course every one of those capital N stock prices will be one of the little n stock prices in our binomial model, that if we could generate this random sample, we could approximate the exact price from the lattice with this. Namely, we just, instead of, we still have the present value, same as the original formula, but where we replace the theoretical expectation using the binomial distribution with an average payoff. And the question then becomes, does this average payoff of the randomly generated stock prices, is that a good approximation to the theoretical expectation? And your instinct would be, well, it would have to be, because these stocks were generated randomly, which means that they are going to reproduce the original stock prices with the appropriate probabilities. And that's all you need for a good expectation.